Morning all, I hope you're keeping well. A number of you have asked me to do a revision session on static rigid bodies, which is one of the more complex parts of the mechanics side of the course. I'm going to take you through the examples on page 142 to 144 of the applied book. It is available on ActiveLearn if you don't have a copy with you at home. So let's take a look at the question. A uniform rod, reminder that uniform means that you can take the centre of mass as being in the middle of the rod, is 40 kilograms long and 40 kilograms and length 10 meters, rests with the end A on rough horizontal ground. So we're going to start drawing that. So here's the drawing that I've got so far. We've got the 5 meters on either side of the centre of mass. We've got 8 meters up to the peg at C, and we've got 2 meters from C to B, and it's a 15-degree angle. The most important thing with these kind of questions is to understand the nature of the other forces involved. So if we think firstly at the peg at C, notice the peg is smooth. If a peg is smooth, any smooth surface can only exert a force which is perpendicular to the plane of contact. So that means that this must exert a reaction force at C, which we're going to call RC, which must be perpendicular to that plane, which is going to be perpendicular to the beam itself. We're going to call that RC. Notice that is not a vertical force, and that's going to come really important later. End A is on rough horizontal ground. So if it's a rough horizontal ground, not only do we have the perpendicular reaction force, which we're going to call RA, we're also going to have some friction force. Now, I know that if I look at the horizontal component of the force, this is going to be pushing it to the left. This RC pushes it towards the left, so I know that the friction force must go towards the right. And I'm going to call that my frictional force down here. I'm going to do it in green. It's my friction at A. Once I've got those forces, the rest of the question becomes a lot easier to resolve. And we do it in exactly the same way every time. We're firstly going to use moments about our pivot point of A, and then after we've used moments, we're going to resolve our forces. We're going to resolve our forces vertically and horizontally, and use the fact that they're in equilibrium. Use the fact that it's in equilibrium to set those all equal to 0. So let's start. So we'll start by taking moments around A. If I look at the clockwise moments, the only thing that's causing this to pivot round in a clockwise direction is this 40G force. Now be careful. Remember, the moment exerted by this force is going to be the force times the perpendicular distance to the pivot. Now I'm just going to mark here in red what that distance looks like. It's this distance along this side of my triangle. It's this red distance which I'm doing with a curvy line. Now if we think this is 15 degrees, this is 5 meters, this distance here is going to be 5 cos 15. So when I do moments about A, I've got my force, which is 40G, times the perpendicular distance, which is 5 cos 15, must equal my anti-clockwise moments, which is this force RC, times by its perpendicular distance. Well, this is a right angle, so it's just times by 8. That then tells me that RC is equal to 200G cos 15 divided by 8, which is 25G cos 15. That gives me an answer of 237 newtons. I'm going to need that more exactly, so I'm going to just store it into my calculator pressing store and then A, and my calculator will tell me it's stored in A. I'm just going to leave myself a little note there to say that that's stored as A. We've now answered part A of the question. To answer part B of the question, I'm going to need to resolve my forces in a vertical and in a horizontal direction. So RA is vertical, FA is horizontal, 40G is vertical. The only one that I'm going to need to resolve is this component RC. Now, we should be able to see that my angle here is also 15 degrees. So, I know that this is 237 newtons, I worked that out. So here, I'm going to have the vertical component is going to be 237 cos 15, and my horizontal component is going to be 237 sine 15. I'm now going to start resolving my forces. It doesn't matter whether I do the horizontal or the vertical first. I'm going to start by resolving it horizontally. Pushing it to the right, I've only got FA. My friction at A is equal to the left-hand component, the leftward component of RC, which is 237 sine 15. On my calculator, I'm just going to type in A sine 15 which gives me 61.25. Resolving vertically, slightly more difficult. I've got RA upwards plus 237 cos 15 must equal 40G. So on my calculator, 40 times 9.8 minus A cos 15 gives me an answer of 163.4 newtons. I'm now going to use the fact that F equals mu R, therefore, F over F equals mu R, so mu equals F divided by R, which is 61.25 over 163.4. 61.25 divided by my answer gives me an answer of 0.375. That's the minimum coefficient of friction allowable for it to be in equilibrium.